Deep Q networks. DQN. In reinforcement learning. AI Advanced Level. Introduction. Q-learning is a powerful reinforcement learning algorithm. But it has a major limitation. It uses a Q table, which does not scale well for large or continuous state spaces. For complex problems like video games, robotics, autonomous driving, the number of possible states becomes too large. To solve this, researchers introduced Deep Q networks. DQN. DQN combines reinforcement learning, deep neural networks. This allows agents to learn directly from high-dimensional inputs like images. What is a Deep Q network? Deep Q network, DQN, is a reinforcement learning algorithm that uses a neural network to approximate Q values instead of using a Q table. In simple terms, DQN equals Q learning plus neural network. Example concept. State means neural network means Q values means best action. Why DQN is important? DQN is important because it handles large and complex state spaces, works with raw inputs, images, sensors, eliminates need for Q tables, enables real-world RL applications, was used to achieve human-level performance in Atari games. Example concept. Deep learning plus RL means powerful decision-making systems. Key idea behind DQN. Instead of storing Q values in a table, DQN uses a neural network. Q, S, A, approximately equals neural network, S. The network takes a state as input and outputs Q values for all possible actions. DQN architecture. Components. 1. Input layer. Represents the current state, can be images, vectors, or sensor data. 2. Hidden layers. Neural network layers. Dense or convolutional. Extract features. 3. Output layer. Outputs Q values for each action. Example. Q, S, A1, Q, S, A2, Q, S, A3. DQN workflow. Observe state. Down pointing arrow. Feed state into neural network. Down pointing arrow. Get Q values for all actions. Down pointing arrow. Choose action. Epsilon greedy. Down pointing arrow. Execute action. Down pointing arrow. Receive reward and next state. Down pointing arrow. Update network. Down pointing arrow. Repeat. Experience replay. One of the key innovations in DQN. Instead of learning from consecutive steps, DQN stores experiences. State, action, reward, next _ state, then randomly samples them for training. Benefits. Breaks correlation between samples. Improves stability. Increases learning efficiency. Target network. Another important improvement. DQN uses 2 networks. 1. Main network. Updated every step. 2. Target network. Updated less frequently. Provides stable Q value targets. Example concept. Stable target means stable learning. DQN loss function. The loss measures the difference between predicted and target Q values. L equals R plus gamma max A single quote Q T A R G E T S single quote A single quote minus Q S A 2 L equals R plus gamma A single quote max Q target S single quote A single quote minus Q S A 2 exploration strategy. DQN uses epsilon greedy policy. Explore with probability epsilon. Exploit with probability 1 epsilon. This helps balance learning and performance. Example Python code. Conceptual. Import torch. Import torch. NN as NN. Class DQN. NN. Module. Def__init__. Self. Super. __init__. Self. FC equals NN. Sequential. NN. Linear. 4. 64. NN. ReLU. NN. Linear. 64. 2. Def forward. Self. X. Return self. FC. X. Model equals DQN. State equals torch. Rand. 1. 4. Q_values equals model. State. Print. Q_values. Applications of DQN. Game AI. Atari games. AlphaGo. Early RL ideas. Robotics. Navigation. Control tasks. Autonomous driving. Decision-making systems. Resource management. Scheduling. Optimization. Advantages of DQN. Advantages include: handles large state spaces, works with raw inputs, images, more scalable than Q-learning, powerful for complex environments, foundation for deep RL. Example concept: neural networks means scalable RL. Limitations of DQN. Limitations include: requires large training data, computationally expensive, training instability, sensitive to hyperparameters. Improvements over DQN. Several advanced versions exist. Double DQN. Dueling DQN. Prioritized experience replay. These improve stability and performance. DQN versus Q-learning. Q-learning uses Q-table. Limited scalability. DQN uses neural network. Scalable to complex problems. Future of deep Q networks. Future trends include: combining DQN with transformers, multi-agent reinforcement learning, real-world robotics applications, improved stability techniques. Example concept: deep RL means autonomous intelligent systems. Concepts learned from DQN. Understanding DQN helps learners understand. Checkmark how deep learning enhances RL. Checkmark how neural networks approximate value functions. Checkmark how experience replay improves learning. Checkmark how large-scale RL systems work. Checkmark how AI solves complex decision problems. Simple definition: Deep Q network. DQN. A reinforcement learning algorithm that uses a neural network to approximate Q values for decision making. Final summary: Deep Q networks. DQN. Extend Q learning by using neural networks to handle large and complex environments. They introduce key innovations such as experience replay and target networks to stabilize learning. DQN has been successfully applied to game playing, robotics, and other real-world tasks. Understanding DQN is essential for building advanced reinforcement learning systems and intelligent agents.